Have you ever watched a drone pilot launch into what looks like a calm sky, only for a sudden 2-5-mile-per-hour gust to send the machine tumbling toward the ground in seconds, costing hundreds or even thousands in repairs and lost footage? That heart-stopping moment isn't random bad luck. It's the direct result of wind resistance and stability problems that have limited drone performance since the technology first took flight. Yet right now, engineers are deploying breakthroughs that turn those same invisible forces into an advantage rather than an enemy. The difference between a crashed quadcopter and one that holds rock-steady position in gale-force conditions comes down to a precise fusion of physics, materials, science, sensor, intelligence, and adaptive algorithms that anticipate chaos before it even registers on your controller. Today, we're unpacking every layer of that battle, so you can build, fly, or choose drones that don't just survive the wind, but dominate it, delivering footage, data, and missions that were impossible just a few years ago. At its core, wind resistance is governed by the drag equation. Drag force equals 1/2 times air density times velocity squared times the drag coefficient times the frontal reference area. That velocity squared term is the killer. A 10 meters per second crosswind doesn't simply nudge your drone sideways. It multiplies drag exponentially, creating asymmetric airflow over the rotors that induces pitching moments strong enough to overwhelm basic stabilization. For a typical lightweight consumer quadcopter weighing under a kilogram, the inertia is low, so even a moderate gust shifts its center of pressure faster than the motors can compensate, leading to drift, wobble, or full loss of control. Headwinds demand extra thrust just to maintain speed, draining battery life by 20 to 40% depending on payload and altitude, while crosswinds generate torque that tilts the entire airframe and disrupts the rotor wake, reducing lift efficiency by up to 30%. Add turbulence from buildings or terrain, and you get rapid gusts that spike power draw another 50%, pushing motors into thermal overload and sensors into saturation. These aren't abstract numbers. They're the reason thousands of missions fail every month. The first line of defense is smarter hardware design that attacks drag at the source. Streamlined fuselages with contoured surfaces and minimized frontal area cut the drag coefficient dramatically, often by 18 to 25%, when engineers apply computational fluid dynamics to smooth every arm, joint, and camera housing. Carbon fiber frames provide the rigidity needed to prevent flexing under load, keeping propellers perfectly aligned even when gusts try to twist the structure. Heavier builds add beneficial inertia that resists sudden accelerations, though engineers balance this against thrust-to-weight ratios above 3:1, so motors still have reserve authority for corrections. Rotor configurations have evolved too. Tilting motors outward by 20 degrees isolates rotor downwash from incoming headwinds, reducing induced pitching moments by 26%. Larger diameter or variable pitch propellers deliver higher thrust at lower RPMs, maintaining efficiency across wind speeds, while toroidal or multi-blade designs further minimize tip vortices that amplify turbulence, giving smoother hover even in gusty conditions, up to 15 meters per second. Powerful brushless motors with high torque curves ensure instant response, and redundant sensor suites, including multiple inertial measurement units, cross-check data, so a single failure doesn't cascade into instability. Sensors make the invisible visible. Every modern drone relies on a tightly fused inertial measurement unit combining gyroscopes and accelerometers. Gyroscopes capture angular velocity around roll, pitch, and yaw axes hundreds of times per second, detecting the tiniest rotation induced by wind shear. Accelerometers measure linear acceleration, including gravity, providing an absolute reference for tilt relative to the horizon. On their own, gyros drift while accelerometers confuse forces, so Kalman, or extended Kalman filters, blend the streams. The result is orientation accurate to fractions of a degree, even when a 1-2 meter per second gust tries to flip the craft. GPS and real-time kinematic positioning add positional lock, allowing the drone to lean into the wind with calculated counterthrust equal to the drag force, maintaining hover within centimeters. Vision sensors and optical flow cameras provide ground relative velocity data when GPS is denied, while emerging wind estimators feed direct airflow vectors into the flight controller for proactive adjustments before drift even begins. The real magic happens in the control layer, where classical, proportional, integral derivative loops meet next-generation intelligence. PID controllers run separate loops for each axis, with the proportional term delivering immediate corrective thrust proportional to the current error, the integral term eliminating steady-state offsets like constant wind push, and the derivative term anticipating rapid changes from gusts to dampen overshoot. Tuned aggressively, these loops achieve millisecond responses, but they falter in highly variable winds because fixed gains can't adapt to changing dynamics like payload shifts or turbulence intensity. That's where adaptive and model predictive control take over. Adaptive PID variants use online gain scheduling or neural network tuning to adjust parameters in real time based on observed disturbances, reducing settling time by up to 45% and energy consumption. Model predictive control goes further by forecasting wind behavior over a short horizon, using onboard wind estimation and solving an optimization problem every few milliseconds to choose the optimal thrust vector sequence that minimizes deviation while respecting motor limits. Reinforcement learning-based deep controllers, trained in simulation across thousands of wind profiles, learn policies that reject disturbances 50 to 65% more effectively than baseline methods, predicting gust patterns from sensor history, and adjusting preemptively so the drone slices through turbulence instead of fighting it. Practical flight techniques amplify these technical advantages. Always launch and land facing directly into the wind to maximize control authority during the most vulnerable phases. Use sport or attitude modes when appropriate to unlock higher speed and thrust reserves, though monitor battery drain because countering wind at full power can slash flight time dramatically. Stick to the 2/3 rule. Never push beyond 2/3 of your drone's rated maximum wind speed for sustained operations, giving yourself margin for sudden gusts that can be 30% stronger than the average. Fly at lower altitudes where wind shear is reduced and visual references are clearer for manual corrections. Plan routes that favor headwind legs outbound so tailwind assists on the energy-hungry return. Pre-flight checks are non-negotiable. Verify propeller integrity, calibrate the compass and IMU, ensure firmware is current for the latest stabilization patches, and confirm battery health above 70%. Apps that integrate live anemometer data or forecast models let you abort before problems start. In the air, gentle stick inputs prevent overcorrection that amplifies oscillations. These solutions scale across drone classes. Consumer models rated for 10 to 12 meters per second now incorporate GPS-assisted hover that automatically leans the airframe to cancel lateral forces, maintaining position with sub-meter accuracy. Professional platforms rated for sustained 12 to 17 meters per second use redundant IMUs, AI gust rejection code, and high-thrust motors, enabling missions like offshore inspections or disaster response. Heavy-lift octocopters with canted rotors and advanced control algorithms have position errors in strong crosswinds. Even extreme examples exist where specialized drones have operated in hurricane-force winds exceeding 100 miles per hour. Their reinforced frames, predictive controls, and massive thrust reserves turning what would be certain destruction into data-gathering success. The payoff extends beyond survival. Stable platforms deliver sharper 4K footage without motion blur, accurate LiDAR scans without drift artifacts, and reliable payload delivery in urban canyons, where buildings create unpredictable micro-turbulence. Looking ahead, the frontier is morphing structures and bio-inspired designs. Drones with variable geometry arms that change shape mid-flight, controlled by deep learning models, can reduce energy consumption in windy conditions by as much as 85% while maintaining perfect stability. Hybrid systems fusing LiDAR wind preview with onboard neural networks will let autonomous fleets navigate entire cities in storm conditions, adapting trajectory and attitude on the fly. Materials science is delivering lighter yet stronger composites that raise thrust to weight without sacrificing rigidity. Mastering these elements doesn't require a PhD or million-dollar lab. Start by selecting platforms with documented high wind ratings and thrust-to-weight ratios above industry average. Log every flight with telemetry to analyze PID performance and wind-induced errors. Then iteratively tune gains or update firmware. Experiment in controlled conditions with increasing wind exposure, always prioritizing safety margins and emergency return-to-home settings calibrated for worst-case drift. Maintain your fleet religiously, because a single worn propeller can degrade stability more than a 5-meter-per-second gust. The pilots who invest in this knowledge aren't just flying drones. They're commanding aerial systems that operate reliably where others retreat, capturing once impossible shots, mapping inaccessible terrain, and delivering critical services in weather that once grounded everything. Wind resistance and stability problems once defined the upper limit of what drones could achieve. Today, those limits are being shattered by the exact combination of aerodynamic insight, sensor precision, control intelligence, and practical technique we've explored. Whether you're a hobbyist chasing cinematic footage, a professional surveyor demanding centimeter accuracy, or an innovator pushing autonomous boundaries, the tools exist right now to make your drone unstoppable. The next time you power up and feel that first hint of breeze, remember, the wind isn't fighting you anymore. With the right engineering mindset, it's simply another variable your machine has already solved. Fly smarter, fly farther, and watch as the sky opens up in ways you never thought possible.